everyone. Great, thank you for having me. So excited to be here in Japan to give this talk. Yeah, let's get going. So I'm not going to assume that anyone here knows what Envoy is, so just a short little agenda. I'm going to start with a brief overview of what Envoy is. We'll talk about Envoy's design goals. We'll do an Arch overview. And then the fun part of this talk, which is something that I don't typically do, is that we will be able to go into some deep dives of some different architectural components of Envoy. And I think there's some pretty interesting patterns there that just from a computer science perspective are fun. And then we'll do some Q&A. So for those of you that don't know about Lyft, because Lyft does not operate here in Japan, Lyft is a US ride-sharing company. And Lyft is a large microservice architecture, but let's go back about 5 years and set the origins of why we made Envoy. And what we're seeing here is Lyft's architecture from about 5 years ago. So this is a very stereotypical, quote, monolithic architecture. So we have clients, we have the internet, we have an AWS load balancer, we have a monolithic application that's built in PHP and Apache, and 5 years ago, Lyft's data store was MongoDB. So this is, again, it's a, quote, simple architecture. We don't have any microservices. But one thing to point out here is that even with this simple architecture, we still have a network, we still have a database. So even at this very early stage, developers are still starting to have problems with trying to understand where problems are actually occurring. Are they occurring out on the client? Are they occurring in the load balancer? Is it something that's going on within Amazon's architecture? Is it a database problem? It can be difficult to tell even at this very early stage. So this is Lyft about 3 years ago, and as you can see, we still have many of the same architectural components. So we have clients, we have the internet, we still have an Amazon external load balancer, we still have our PHP and Apache monolith. But as you can see now, we started to introduce a lot of other components. We have HA proxy as well as NSQ to add some queuing. We now have a whole array of Amazon load balancers. We now have 2 data stores. We're using MongoDB as well as DynamoDB. And at this time, we have probably around 30 different Python microservices. And from an operational perspective, this architecture is probably an order of magnitude or more complicated than the one that I previously showed. And it's more complicated mainly from a debugging perspective. When a problem occurs, where is that problem happening? Is it happening out on the internet? Is it now one of our 30 or 35 different Amazon load balancers? Is it an application problem? Is it a database problem? Super hard to tell. And what people find when they're building these microservice architectures is that actually debugging them and actually operating them, that is the difficult part. Very easy to write microservices, very hard to actually get them running in production. So let's dig deep now and let's try to understand 3 years ago what were Lyft's main problems. Lyft, like most companies or most modern companies, is what I call a polyglot architecture. This means that even multiple years ago, Lyft was writing code in PHP, in Python. I think we had a Java service maybe. We were starting to talk about writing services in Go. And the days of companies picking a single language and writing all of their services or all of their systems in one language is mostly done. It's just not the way that people in the industry are doing it now. Much more common that companies are allowing developers to write their systems in 3, 5, 6 different languages, or companies acquire other companies that have written their systems in different languages. So now by acquisition, we have 4, 5, or 6 different languages. So we're dealing with this polyglot architecture where we just have lots of different code, lots of different frameworks. Modern internet architectures are built using different protocols. So obviously we have HTTP1, HTTP2, we have gRPC, but then we have many different databases, we have different caching systems, different streaming systems. So these architectures are becoming increasingly complicated. Load balancers are a critical component of modern systems, and in the industry today, there's a huge array of different load balancing systems. So we have traditional load balancers from hardware vendors like F5. We have software load balancers like HAProxy and Nginx. We have cloud vendor solutions like the AWS ELB. And these load balancers all have different features. They all output different types of stats and observability data, and this can make things quite complicated. And as I was just mentioning, what you start seeing with each of these points, from a polyglot architecture with different frameworks to different protocols to different load balancers, and you'll hear me talk about this a lot, is observability is really key. Because when you're operating these microservice architectures, having a consistent set of stats, logging and tracing is what allows you to really understand what's going on within your system. And because of this heterogeneous architecture, nothing is consistent. So when developers are trying to understand what's going on, it's what I call cognitive overload. So you're trying to put together all of these disparate pieces of data, nothing quite matches, and that can be quite complicated from a debugging standpoint. From a distributed systems perspective, as distributed systems developers, we are told that we need to do things like retries and circuit breaking and rate limiting and timeouts. But if you look through different companies' code bases, you'll see that some of these things are missing, or the implementations are different. And again, from an operational perspective, it's super critical to have consistency here, because when you're debugging things, you would like to know that the same retry implementation is being used, or the same algorithms are being used. So it's both having consistency of implementation and whether these things are implemented at all. So again, we're told as developers that we should have authentication and authorization. Most companies have that at the edge. Obviously, they're doing TLS and they're doing a couple other things. But the status quo at most companies from an internal architecture perspective is very few companies actually have authentication and very few companies have authorization. So these are things that we know that we would like to have, but most people don't have them, and that's a problem. So getting back to the multiple languages, the way that historically most companies have solved this array of problems is that they've built sophisticated libraries. So Netflix has a set of libraries called Histograms. Twitter did a library called Finagle. Those are both Java libraries, but these are libraries that incorporate a lot of distributed system best practices around making service calls, around doing retry, circuit breaking, rate limiting. But you'll see this theme here, which is that those libraries are only in Java. So what do you do if you have Python? What do you do if you have Go? You're basically out of luck. So you're left with this option, which is either I have to re-implement this library in every different language that I'm using, which is very resource intensive, though some companies have done it, or we need to look for a different solution. And this gets, again, back to debugging. As I was saying before, is when we're operating these microservices, primarily we need to debug when things go wrong. And we spend a lot of time as developers debugging latency as well as failures. So if we don't have this rich observability data and it's not consistent, it can be very, very difficult to actually figure out what is going on. And this brings us to what happened at Lyft about 3 years ago, and I've seen this at a lot of different companies, where companies will say, hey, I am reaching my scaling limits of my microservice architecture. of my monolithic architecture, I would like to roll out microservices. Let's do it. They roll out some microservices, but then they start having problems. They start having networking problems, or they start having random failures or latency, and they don't know how to actually debug it. So what happened at Lyft about 3 years ago is we had our monolith, we had 30 different microservices, and we had reached a point at which developers did not trust the microservice architecture. They were no longer willing to build critical functionality into microservices. So now they were saying, nope, I'm not going to make new microservices. I'm going to keep adding code to that monolith. So now we are in really the worst possible world where we have microservices. We have to maintain those microservices, but developers don't trust them. They don't want to use them. And they're going to keep adding code to that monolith. So where does this leave us? This leaves us with lots and lots of pain. So let's see if we can do better here. So this brings us to Envoy. So the catchphrase of the Envoy project is that the network should be transparent to applications. Obviously, problems are going to occur when we're dealing with these, these architectures where things are changing all the time. We're dealing with auto scaling, we're dealing with failures. Problems will happen. So let's try to make the network transparent. But when problems do occur, let's try to figure out what's actually going on. One thing to point out here is that from a modern internet company perspective is, people spend a lot of time working on infrastructure. We have lots of talks on things like Envoy or databases or Kubernetes or things like that. But the honest reality is that to most companies, for time that you're spending on working on infrastructure, that's total overhead. You're not making any money working on infrastructure. What you really want is you want all of your application developers to be working on business logic, because that's when your company is actually making money. So the way that I look at infrastructure software is that we want to hide the infrastructure from application developers so that theoretically they can spend 100% of their time working on business logic. So how do we do that? So Envoy design goals are, based on what I had already brought up, about some of the problems of a library-based solution. You have to go through and you have to implement those libraries in every different language. I don't know how many of you have worked with libraries, but actually going through and having to deploy library changes to multiple hundreds of services, it can take months and months and months. It's an incredibly painful process. So with Envoy, we decided to do what we call an out-of-process or a sidecar solution. So that means that we want to build a bunch of functionality into Envoy, but we want to make it a self-contained server. And we can run that alongside every application, and we can build a bunch of this common difficult functionality into it so that we don't have to re-implement it in every different application language. Because we're going to spend a bunch of time doing this, we might as well make it fast. So let's focus on low latency. Let's make it high performance. Let's try to have developer productivity. In early 2015, that led us to using C++ as the implementation language. At its core, Envoy is what I call an L3 or an L4 byte proxy. So that means that it is a TCP proxy or a byte-in, byte-out proxy. And that's very important because many proxies these days, they really focus on REST, they focus on HTTP, and of course, those are very important protocols. But as we discussed before, we use Redis, we use MongoDB, we use Kafka. So we would like Envoy to ultimately be able to work with different protocols because, as we'll see, there's a bunch of cross-cutting or common concerns that we can build into a proxy that will work in a protocol-agnostic manner. But as I was saying, HTTP is very popular. We build many different APIs using REST. Obviously, we're building gRPC APIs now. So that is a very important part of modern internet architectures. So from a filter perspective, Envoy has a very sophisticated L7 HTTP stack. And that allows us to write filters on concepts, not just bytes, but things like headers, body, stuff like that. Envoy is an HTTP 2 proxy first, so at the time that it was originally written, it was actually quite novel that Envoy was able to proxy in both directions, from H1 to H2 and from H2 to H1. And at this point, other proxies are finally getting that functionality, but at the time, that was a design goal of Envoy, because we wanted Envoy to be usable for gRPC, which requires proxying HTTP2 in both directions. Another primary goal of Envoy is to have it be, have all of the configuration discovery be API driven, and this is super, super critical. If you look at the way that historically people have deployed most proxy servers, is they have the server, they're going to deploy them onto different hosts, and then each of those servers actually ends up having its own configuration file. So you have to manage a process using Salt or Puppet or something else, or your own homegrown system, to actually take those files, spray them out to every host, and actually load them up, and that can be very painful. So from Envoy's perspective, we wanted to build a system where we can have a central management server, have an API that anyone can write to, and then have Envoy be an independent component that can be built into other people's architectures. So having an API first configuration system was quite important. Envoy focuses on both active and passive health checking. So active health checking is the idea of sending a health check request to a backend host. Passive health checking is monitoring the performance of backend hosts as we go. So those are things like consecutive 500s, or looking at latency outliers, or stuff like that. We have already talked about things like retries and timeouts and circuit breaking and all of that stuff. So we would like to build all of that into Envoy so that we can do that once and not have to implement that in every different application language. And again, you'll hear me say this again and again and again, but observability is really key. So that's stats, logging, as well as tracing. We would like Envoy to have best-in-class observability so that as we're debugging problems, we can really understand what's going on. We can have that observability data be consistent across our entire architecture. We would like to use the same software for our service proxy, our middle intermediate proxy, or our edge proxy. This is important because historically people have used different proxies at different places in their architecture. For example, they might use Nginx on the edge. They might use HA proxy on their internal nodes. Those are both great proxies. But that means then from an operational perspective that you need to learn to operate different pieces of software within your architecture. So the more, really, again, it comes back to cognitive load. The less software you can use, the better you can learn to operate it, the less issues that you will have. So a design goal of Envoy, and in fact, if you look at it, most of what these different proxy deployments do, service, middle, edge, they're all basically the same. So we want to be able to use the same software in all of these places to make operations easier. Finally, we wanted to allow Envoy to do what we call hot restart, which is to restart Envoy in both a config and a full binary reload without dropping any local connections. And that's important because obviously now in a container-based Kubernetes world, we can do different types of rolling deploys, but many different architectures are actually not using Kubernetes yet, and they still run on VMs or on bare metal. So from a deployment and operations perspective, being able to actually restart Envoy without dropping any connections is quite powerful. So this is a high-level block diagram of Envoy. And what you'll see here is that, Envoy really at its core, one of our goals is to have it be extensible. So we allow people to write filters at different layers of the stack, and they can use filters to plug in functionality to implement new protocols, to add things like rate limiting, to modify connections, to add different types of authentication. So from a data plane perspective, that's the top section. What you'll see is that we have a concept of a worker. The workers host listeners, so listeners are things that listen for connections. Our first extensibility point is listener filters. So these are filters that run on connections before the connection actually being accepted. So then we have a connection. Once we have a connection, we have a filter stack at the TCP layer. So we have both read filters and write filters. So this is the place where we could implement TCP rate limiting, or we could implement MongoDB, or we could implement HTTP. And then shown here is the HTTP stack, where on top of that we have a TCP filter for doing HTTP processing. And then, as I was saying before, we have a whole separate set of filters for processing on headers or body. And then we have a router, and the router integrates with the backend of Envoy, which is all of the upstreams that we can proxy to. So from an upstream or a backend perspective, we have a thing called the cluster manager. The cluster manager manages clusters of hosts. So from Envoy perspective, a cluster is a single grouping of backend hosts. So at Lyft, for example, that would be the location service or the pricing service or the user service. So it goes cluster manager to cluster to backend host. And then Envoy has a whole bunch of connection pooling logic, and then we'll eventually flow through this entire thing and we will proxy our data. Now, so we have these workers. And then we also have some common functionality that is core to the entire server. So these are things like stats. There's an admin processing engine, so you can get on the box and you can do various types of debugging. We have management systems for clusters, listeners, routes. And then we have what we call our XDS API. XDS is our configuration API, which I will talk about next. All right, so what is XDS? So I talked about before how, you know, a core real tenet of Envoy is that we can make it API configuration driven. So the way that we talk about it is that Envoy is a universal data plane. So the idea is that we don't want to tie Envoy to only working with Kubernetes, or only working with console, or only working on bare metal. We would like Envoy to be a Swiss Army knife solution that people can build different systems on top of. And what you've seen now, I won't have time to go into this, but people have done that. We have people using Envoy in a huge variety of different situations, from cloud vendors to on-prem to people building products on top of it. So, you know, the idea is that we can take this system, and because of these APIs, people can build different management servers, and they can customize Envoy to work in their environment. So XDS is just something that that we started calling all these APIs. So that's the Star Discovery Service. So we have various different APIs here. So examples of that are LDS, which is the Listener Discovery Service. That's how we look at, you know, are we going to have a MongoDB listener or an HTTP listener? We have the CDS, or the Cluster Discovery Service API. That's how we have different upstream clusters. And one cool thing here is that in the current code, we have these APIs. The APIs are defined in Proto 3. The really amazing thing about Proto 3, and in fact, you can talk to me after, but I'll talk about Proto 3 all day. It's a very cool technology. One of the really nice things about it is that with one API, you can have both a gRPC API and you can have a JSON YAML API. And that is super, super powerful. So it means I can have a well-typed API, and I can allow people to build their management servers however they want. If they want to use YAML or JSON, they can do it. If they want to use gRPC, they can do it. And that is really powerful. As I was saying before, we would like to avoid what I call this, this per proxy config hell. So, having to generate configuration files for all my proxies and get those onto different hosts can be very painful. So this allows us to have a central management server and actually, have the configuration be driven from that server. And what that really means is that I can deploy Envoy, I can deploy what we call a Bootstrap configuration for Envoy on every host. When Envoy loads, it'll look at its local environment. So for example, it'll look at what region it's running in, or it'll look at what its node ID is. And then when it boots up, it'll contact the management server. It'll say, hey, I'm here, I'm node A, I'm in region B, give me my config. And this allows the backend configuration server to customize the configuration that is given to the Envoy. So it can customize it based on its cluster, it can customize it based on its region, it can customize it if it's a test host. So that's very powerful. And again, that allows us to build services for configuration and not have to worry about all this orchestration where we're trying to get these config files out to different hosts. So that gives us, again, Envoys plus XDS, plus this management system. We've taken this cobbled together proxy system, which many companies have typically used, to now we have a full proper distributed system. We have a fleet of Envoys, we have a management system, so we have what I call a fleet-wide traffic management system, which is great. And you'll hear me talk about this more, but Envoy is really built from the ground up, from an eventually consistent perspective. And that's important because what many people don't realize is that really everything about modern internet architectures is eventually consistent. Like, people would love to be able to know a snapshot of, oh, these are all of the hosts that are here at this time, or these are all of the healthy hosts. But the reality is that that's not really possible. There's network partitions, there's auto scaling, so the whole system is inherently eventually consistent. So instead of trying to paper over that, instead of having the whole architecture attempt to be consistent, we just embrace the fact that it can't be. And this actually makes a bunch of programming things easier, and it actually makes Envoy scale better, which we'll talk about more. All right, let's step back for a second. Let's talk about Envoy's threading model, and let's talk about what people in the industry have called C10K. So C10K was a paper that was written in the early 2000s. It basically stands for 10,000 connections per box. And in 2018, 10,000 connections per box probably sounds very, very, very laughable, but in the early 2000s, that was big. So prior to about 20 years ago, the way that most people wrote networking servers, whether they were proxies or databases or something else, is they would use what we have there on the left side, which is the connection per thread model. And that was popular for the primary reason is that it's very simple. It allows the programmer to think in a fully synchronous manner. You call read, you call write, you have your little local loop per connection. So it's very simple to actually to reason about. And so this is the way that people wrote software for many, many years. It became very clear in the late 90s or in the early 2000s that this would not scale. The reason that it wouldn't scale is that from an operating system perspective, for every thread you have to maintain stack, so that costs a bunch of memory. You have to do context switches, that costs a bunch of CPU. So people were realizing, hey, we would like to have long-lived connections, it's good for performance, we would like to have tens, hundreds of thousands, even millions of connections per box. Probably can't do that using connection per thread. So in the early 2000s, that really fell out of favor, and primarily driven by Nginx, we moved to the right side, which is the async programming model. And that is to have a thread, to have an async event loop, and then to have multiple connections per thread. And this scales much better because now we don't have to do context switches. We don't have to have a stack per thread. And what we can actually do there is that now, again, we can have many, many, many different connections. The problem is that this is much more difficult to actually program. So we've traded programming difficulty for scalability and perf. But this is really the way that all modern servers are actually written. So from Envoy's perspective, when we started in 2015, obviously we were going to do the event loop model. So this is Envoy's threading model. And the thing to point out here is that we have two different concepts. We have what we call a main thread, and then we have a worker thread. So the worker thread is the actual data plane thread. So that's where we have listeners, that's where we have upstream connections. And typically what we do is, because we assume that the worker threads won't ever block, by default in Envoy, we boot 1 worker thread per hardware core. So if your machine has 8 hardware cores, we will boot 8 different workers. What we have is that those worker threads are what we call embarrassingly parallel. So that means that from a concurrency perspective, we would like there to be no locks. And that's important again because if you look back in the early 2000s, sure, people were doing multi-core programming, and there were boxes that had 2, 4, 8 different cores. But now we're in a situation where if you look at the larger companies, we have data center servers which now have 90 plus cores. So it is increasingly common for people to run server software on 90, 100, 200 cores. So at that core count, actually starting to look at how we do locking becomes quite important. So that's the actual worker threads. On the main thread, we have a bunch of functionality which is low rate but very important. So that's XDS configs, that's runtime feature flags, flushing stats, admin processing, process management, like handling signals. And the idea, or the reason that we've bifurcated this between the main thread and between these worker threads is that it's mainly for simplicity. So on the main thread, because it's effectively single-threaded, we don't have to worry about locking. And again, on the worker threads, because we pretend that they're all single-threaded, we don't actually have to worry about locking. So it's a core theme within Envoy is that we try to hide all of the concurrency complexity from programmers as much as possible. So the majority of Envoy code, even though it's highly concurrent, programmers don't need to worry about concurrency. They write code as if it's actually single-threaded. One interesting point is that, so this type of architecture where we have an event loop architecture, obviously that event loop, if we block, bad things happen. We like to think that modern operating systems actually are built for this type of async programming. Turns out that that's not quite true. There's certain operations, particularly around file I/O, where even today, you can do non-blocking I/O, and you can attempt to write to a file, and it can actually block. And this is particularly problematic in virtual infrastructures. And so what we saw originally with the file I/O is that even though we were doing non-blocking I/O, we actually were blocking, and this was causing us major issues. So there are a few situations in Envoy where we have to do I/O on other threads, and these are particularly around file I/O. So when we're writing, for example, access logs, we do have a set of file flush threads, and those threads handle file I/O, and we do this with appropriate locking so that we can make sure that the main worker threads don't ever block, because as I was saying before, this entire architecture is really predicated on those worker threads not blocking. If they block, then we're going to have high latency and things are just not going to work very well. But the overall idea here is that we can scale this architecture to really an infinite number of hardware threads. We would like Envoy to be able to be run on hundreds and hundreds of threads if people want. All right, so this gets us into something that I think is very interesting. It's called RCU, which is called Read, Copy, Update. This is a locking primitive. It is used heavily within the Linux kernel. And this is a locking primitive that allows you to do read-write locking, but it's for read-write locking that's very read-heavy. So we're frequently reading, we're not frequently writing, and we can do this without any locks. So it's it's a little hard to actually wrap your head around, but it's very, very cool. So the way that this locking primitive works is that there is the concept of an updater. So there's someone that has some data. So from Envoy's perspective, this data could be a route table, it could be a set of upstream hosts. And in practice, this is ref counted data. So let's say that I have a route table, and I'm going to make a new route table that points / to food service. So what I'm going to do is I'm going to make this new route table, and then what I'm going to do is I'm going to go through my copy process. So during the copy process, what I do is I take this ref counted data, I increment the ref count, and then I post that data over to all of my worker threads. Now, remember that all of those worker threads are running an event loop. So the event loop is going in circles. There's someone that's reading on that event loop. Now, the key to RCU is this thing called the quiet period, or the quiescent period. And the idea here is that if we can update the data when we're sure that no one is actually reading it, we can do that without using any locks, and that is super cool. So what that means is that if I have hundreds of threads and they're all going in this event loop, I can make some new data, I can post it over to all of my worker threads, and because the post actually doesn't happen, it doesn't actually occur until that quiescent period when no one is actually using that data, I can be sure that no one, for example, is looking at that new route table. And then what actually happens is that when that data gets swapped, someone that's using that data, if they have a ref count or a pointer to the old data, they'll just keep using it. But the next time they go and they fetch that new data, they will get the new info. And that might be a little hard to understand. I'm going to explain it again in the next couple of slides. But this is a very, very powerful primitive that, again, allows us to do read-write locking without using any actual locks. So this means that it can scale to extremely high core counts without issues. All right, so the next concept is TLS. So this stands for Thread Local Storage. This is another core primitive within Envoy. So there are many different subsystems within Envoy. So these are things like the route manager, the listener manager, the cluster manager. And it's a very common paradigm within Envoy that I'm going to do some stuff on the main thread. Again, maybe that's a new route table, that's some new host information, maybe I'm doing health checking and I'm updating host health status. But I need this data to be available on all of my threads, right? Because when I'm doing, when I'm actually making load balancing decisions, I would like to be able to use that host information or that route table, but I would like to do that without taking any locks. And I would like it to be very fast. And again, like we were talking about before, from an RCU perspective, this is read heavy, so the data doesn't change very often, but it's read very often. So the way that this works is that effectively TLS is a vector of slots. And for the purposes of Envoy, each of these slots is really a reference counted pointer. So what we're seeing here is we have 5 different slots. Let's say that slot 3 is our route table. And let's say that I have a process that is updating my route table. So on the main thread, I might come through and I'm saying, okay, like I've got some new routes. I'm going to take this new route table, I'm going to stick it in slot 3 on the main thread, and then using RCU, I'm going to post that data to all of my worker threads. So I send a post message, I send this event over to all of my worker threads, 1 through 4, and then if someone goes and reads that route table on the worker thread in slot 3 before the post gets there, that's fine. They'll just get the old route table, eventually consistent. If the post then gets there and then someone reads it, they will get the new data. But the idea here is that I can update all of my information across my workers in an eventually consistent way. And again, I can do this without taking any locks, which is super cool. So this again will scale to very, very high core counts. So to make it super clear, let's go through a concrete example. So what we're seeing here is again, it's a complete example of using TLS as well as RCU for cluster updates. So in block 1, we have the cluster manager. So like I was saying before, the cluster manager is the thing that will manage all of my upstream clusters. Clusters contain hosts or backends. Now, those hosts or backends, they can change for various reasons. They can change because we've had some health checking change. They can change because we had a config change, or if they're using DNS for service discovery. So if either there's a health checking change or a config change, on the main thread, Envoy will build a new host set. And then what it'll do is it'll post that new host set, which is really a reference counted vector of hosts. It'll post that over onto the worker event loop. And then at some point in the future, the post handler or the TLS update handler will run. And like I was saying before, if someone needs to read that data before the post gets there, that's fine. They will use the old data. If they read it after, they will get the new data. That's fine, eventually consistent. And then in 6, right, we've got this TLS process. And then during load balancing in point 7 or in block 7, we have the IO event, we have the load balancer. So when a request is coming through and we have to pick a new host, the load balancer will use TLS. It will look in the TLS slot that contains that particular host data, and then it will get that current data. So again, really the key point here is that we've done this without taking any locks, so this can scale to a very high core count, which is pretty cool. But it also means that the system is eventually consistent. Again, it might be a little hard to wrap your head around, but even within the Envoy process, because of the OS scheduler, it may not even be true that every thread in Envoy has the same host data at the same time, right? Because there's no guarantee that the post handler will run at the same time on each thread. So you might be in a situation, of course on the same host, this is within a matter of like microseconds. But you might be in a situation where there's a tiny interval of time where worker 1 sees the old host data, worker 2 sees the new host data. But when worker 1 runs that post handler for that TLS update, it'll swap and then everything is now consistent. So very, very scalable. All right, let's jump to hot restart. So like I was saying before, from an operations perspective, in an optimal world, we would all be using Kubernetes, we would all be using containers, we would all be using blue-green deploys, and life would be super perfect. But unfortunately, for many people, that's not the current reality. So we would, like to be able to do a full binary reload without dropping any connections. And again, this is very useful, from a quote legacy perspective. So what we see here is the 2 different deployment models. So the first model is a Kubernetes or a blue-green or a rolling deploy type model, where I'm going to have a load balancer, I'm going to have some orchestration, I'm going to switch from service A, version A to service A prime. From a hot restart perspective, I'm just going to swap on the same box. I'm going to swap from A to A prime, and I'm going to do that without dropping any connections. So, that's, again, from an operational perspective, that is super useful. So how does hot restart work within Envoy? One of the interesting things is that Envoy actually keeps its stats in a shared memory region. And this is done, so stats are counters and gauges. We'll talk a little more about histograms in a sec. And you might ask, okay, well, there's a bunch of complexity here. Like, why would we keep our counters and gauges in shared memory? It's actually very important to keep gauges in shared memory if you're doing hot restart. The reason is, let's say that we have a gauge for the current connections. And then let's say that we're doing a drain period where I'm going to hot restart my new Envoy. I'm going to let it run for like an hour. I'm going to let the old process drain. If we don't share the gauges between the old and the new process, and let's say that my Envoy is hosting 100,000 connections. I would hot restart. I would immediately see the connection count drop to 0. So from an operations perspective, that's actually pretty bad, and it can be very confusing. So we wanted to keep stats consistent between both processes, and the only way to do that is to keep the stats within shared memory. So Envoy has a shared memory region. There's a stats block in there. We also have various locks for allocating stats out of shared memory, for doing certain types of access logging. And then the way that it works is that we boot up the new Envoy. We actually have a protocol that runs over Unix domain sockets. We have the processes talk to each other. They actually do socket passing. They'll pass some stats. They'll actually figure out if they're running a compatible version. So they'll do this dance where the new process comes up, it'll get itself ready, it'll do its first health checking and config pass, and then it'll say to the old process, hey, I'm up, I am ready, let's start draining. So then the old process will start draining, the new process will be taking connections, and then after some period of time, the old process will actually shut down. And one of the key things here is that this mechanism was built for containers. There are various ways that hot restart functionality has been done in the past, but typically it's been done within the same process. So the process will do some funny stuff of forking and execing. The problem is that doesn't work with containers, right? Because we would like to deploy a new container, the container has to be torn down. So from a container perspective, the process has to be immutable. So we need the new container to come up and talk over Unix domain sockets, and then the old container can be torn down. So because we're moving to a container world, we just made the decision in 2015, let's build this hot restart functionality for containers. And there again, people are moving towards Kubernetes, but there are people that even within containers still use hot restart. All right, so let's talk about stats briefly. So in Envoy, we have a fairly sophisticated stat system. I would say that Envoy does a lot of stats. We have lots of counters, we have gauges, we have percentile histograms. And because, as I was saying before, observability is so important, we spend a lot of time doing this. And because Envoy spends so much of its time actually incrementing stats and computing different histograms, we would like it to perform well. So some concepts. We have store. So a store is the component in Envoy that stores stats. We have syncs. So these are the protocol adapters that Envoy can use to write stats out. So those are for things like statsd, or we actually have a gRPC metrics API. We have an admin system that allows pull access, so you can go to a /stats endpoint and get your stats. We do that in Prometheus format, in JSON format, and I think now in a couple different other formats. And then we have a flushing system, which allows stats to be pushed. So from a stats or a metrics perspective, the observability world is a little split. Some people push, some people pull. So Envoy doesn't want to be opinionated about that. So we allow people to either pull or push. And then the last concept is a scope. So a scope is a grouping of stats that can be torn down together. This is important because, again, Envoy, you can really reconfigure almost all of Envoy without shutting it down. So we can delete listeners, we can delete clusters, we can add them. So in order to not leak stats, we have to have a grouping of stats, which we call a scope, and then we can delete all those stats together. So let's put all of this together. Let's look at how we do stats using TLS, RCU, and all the other stuff that we've been talking about. So stats, again, we keep counters and gauges in shared memory. We keep histograms in process memory, mainly because histograms are substantially more complicated, and because it's not as important that we have consistency between processes for percentiles. So the way that this works is that, again, because we want stats to perform very well, when a worker thread needs to use a stat, it'll look up a stat in the local scope cache. So that's over there on the right. And this is done without locks. So we'll say, okay, do you have this gauge? If the gauge is there, it will actually go through and it will take that gauge back. If the gauge is not there, it will go to the central cache and it will say, do you have this gauge? If it has already been created, it'll be populated in the local TLS store, and then we will use that from then on. If it hasn't been created, we will actually go through and we will make that gauge and we'll populate it in the local cache. And then when we actually need to delete a bunch of stats or delete that scope, we use TLS because all that local cache is in the TLS vector. And then we'll say, oh, I'd like to delete scope A. I will post a message to all my worker threads. Please delete flush your cache for scope A. And that's how we can keep everything consistent without leaking any memory. So finally, let's look at histograms, because this is actually pretty interesting. So from a histogram perspective, again, we don't keep histograms in shared memory, but we would like to do histograms lock-free. So histograms are used for percentiles. So the way that we do this is that we have a parent histogram that's owned by the main thread, and then we have a TLS histogram that's on every worker. And each TLS histogram has two storage locations. It has histogram A and histogram B. So what's pretty cool here is that when a worker thread wants to go and it wants to store a particular value, say backend latency is 20 milliseconds, it will look at the current histogram, which might be histogram A or histogram B, and it will return that local histogram. And this again can be done without locks. Very cool. Now, of course, we have all these histograms that are on all these worker threads. So eventually we have to go through and we have to merge these. So the way that the merge process works is that the main thread says, hey, I would like to do a merge. So the main thread will send a message using effectively RCU or a TLS post. It will post a message to all of the worker threads and will say, hey, please swap your current histogram from A to B or from B to A. And then tell me when you're done. So it's a barrier. So what happens, which again is pretty cool, is because the main thread has sent this message over and isn't doing anything until it knows that we've swapped from A to B, once all of the worker threads check in and say, hey, okay, I'm done, I've swapped from A to B or from B to A, now on the main thread, I can go and I can merge all of the old histograms. So if current now points to A, I can go through B and I can merge all of those histograms, and I can do that without taking any locks. So now we can, again, and this scales to a huge number of threads. So this is quite cool. So this uses, again, these concepts of TLS, RCU, etc. Cool. So a brief summary. So from an Envoy architecture perspective, we have, in general, a bias towards developer productivity. So we would like people to be able to write code quickly, but we'd still like it to be very fast and low latency. Again, the architecture is embarrassingly parallel, and we make all of the hot path as lock-free as possible. Heavy use of RCU and TLS, designed for a containerized world, very extensible platform. I have written actually detailed blog posts about most of this, so you can find that on my Medium account if you'd like to have more information. And thank you very much. I'll be taking questions now, and you can ask me questions on Twitter. And in general, we have an increasingly large community around Envoy. The uptake has been super incredible. We've been open source for over 2 years now, and it's been great. So thank you for having me, and I will take questions now. Thanks. Yep.
How did you actually find that out? And
Yeah, so first it's I've been bitten by this before, but how we found it out is that we have various watchdog timers within the Envoy process. So every worker thread, we have we'll have like a miss watchdog timer that we call a mega miss watchdog timer, and you can actually configure that, and that just checks in, say, every 100 milliseconds or every 1 second. I think, I forget now exact details, but we were using one instance type within EC2, And I think we noticed that we started getting basically 1 or 2 second pauses. So like we would be getting Watchdog mega misses. And I believe we tracked it back to, it was like some SSD instance type, and it's like the power virtualized driver was blocking or something when Linux said that it wouldn't, or like something along those lines. But since then, this has actually been reported by a lot of different people in different types of environments. So I think we've been bitten with it in production, but I think it's just important to have all the timing data, to be able to know when your event loop is actually blocking.
Right, and so you think this is like something that is not specific really to AWS, it's something that is reported a lot?
I do not think it is, I think it's a general problem. I think if you just do some Googling around like Linux non-blocking I/O problems, you'll see a lot of anecdotes. I actually think there might have been a blog post by the HA proxy people recently about this. It's a problem that's been reported by multiple people. It's basically that the Linux non-blocking file API, it doesn't work so well. Yeah.
No. The question was, he's planning to use Envoy and Kubernetes, but is it better to always use it with Istio in the control plane or other?
That's the question that everyone wants to know. So there is a giant ecosystem growing up around Envoy. I think Istio launched last May, so it's been like a year and a half. I think Istio has a lot of momentum, a lot of people behind it. But there are lots of other solutions now. Like there are people that are building their own control planes. There's the Cilium project. There's the people at Solo.io that are building their own platform. There's startups that are building platforms. So what I would say is that Envoy is a complicated piece of technology. And the way that I generally talk about it to people is I don't think Envoy is designed for people that don't really understand, that don't understand networking fundamentals well. So I think that depending on the sophistication of your company, many people have had great success like building directly with Envoy, and that's perfectly fine. I think that if you're on Kubernetes, I think at this point I would definitely look at Istio. I can talk more about it offline. But I think Istio is interesting. I would look at the Cilium project. But I think there's a bunch of different solutions, and I think they all have pros and cons right now. So, yeah. Sorry, what's that? Next big challenge?
The challenge for Go.
Go plus plus. Go plus plus.
I wouldn't say right now that there's one goal or one challenge. I think this has been a really interesting journey for me, and I think it's mostly around, we have had so much success from an open source perspective. Like it's been more than I ever could have possibly imagined. So I actually think that the goal is to continue to see the overall community grow. Like I think that we've done a fantastic job of making people feel welcomed, of allowing people to build different architectures on top. So there's not one technical goal. Like I think, you know, we're going to do some interesting features. We'll probably build Kafka support. I still would like to do what I've been calling like a tap dump filter, so like TCP dump for Envoy at L7. I think there's lots of features that will end up coming, but from my perspective, I want to make sure that the community stays growing and supportive of like the companies, the startups, the cloud vendors. So that's just making sure that we have documentation, that we have a supportive community, that we have enough maintainers so that I don't die. It's a complicated process. So yeah.